I'll be walking you through an implementation, a simple implementation of some of the key concepts in an object detection model, and I intentionally picked one of the easier approaches, and I picked YOLO version 1 for this specific one, because it shouldn't be about implementing really a state-of-the-art model, which I don't think we can cover in half a day tutorial. It's more about giving you an idea of some of the key concepts and how to implement them in PyTorch. So at some points there are a few shortcuts, but we'll still be producing a working object detection model in the end. And this whole tutorial, is in a Jupyter notebook, and it's the third Jupyter notebook you find in the GitHub repository, which we were sharing earlier. The way this is structured is so there are a few parts to building your own model, and all of the code here, or most of the code here, is actually something we implemented. I to be honest, I looked around and checked what's out there available, and I think that's always a good start. Has somebody implemented something that fits my needs? We were talking earlier about, should I go with TensorFlow or should I go with PyTorch? I think sometimes you need to look at both. Honestly, if your goal is not to write something from scratch, but to reuse the state of the art, because sometimes they have been implemented in TensorFlow, sometimes they have been implemented in PyTorch. YOLO, for example, is actually implemented in Darknet, which is a C or C++. I don't actually know. It's a C++ framework. It's a C framework, even better. And so there are some ports, and my goal, and to be absolutely honest, some of the ports you find for some of the models are just not the quality you need for any production purpose or any enterprise purpose, more academic than anything else. And at the same time, we were looking for something that's simple enough to walk you through today. So those with enough quality often come with bloated annotations, with parameters you may not necessarily need. So this is something we implemented for the tutorial from scratch. It'll walk you through some distinct steps. Step one is we'll be pre-processing. We'll be using the Pascal VOC dataset. We'll be pre-processing it in a format that can be read by the model, which is a very distinct format. When we were talking about earlier, is there a data loader or anything available for specific data sets in PyTorch? I think it's difficult anyway, because you have to bring always the data. You have to not just pre-process it, but you have to bring it in a shape that your model is actually expecting. So every model expects, to some extent, a different type of data format. And that's what we'll be doing in step one. And the next step then will be define the loss function, and that is actually most of the work. So we were looking at architectures or model networks. It's pretty simple. You reuse a lot, you change maybe one or two layers, and that's it. The challenge lies in some of the custom implementations you have to come up with, and in this specific case, for example, coming up with a custom loss function is most of the code actually. And then the final thing is we build a network, and we do some transfer learning. We use VGG16 with pre-trained weights, so we don't have to train from scratch. And then we change part of that network so it actually produces the output we are expecting. And while doing that, I walk you through some of the concepts that are interesting in PyTorch. Another point I wanted to make is we were looking into the basics earlier. Mo was walking you through some of the basics of tensor calculations, and I think that's really the most challenging part, and where lots of the work actually is happening. The moment you start implementing something custom, like a loss function, you have to be very familiar with some of the tensor computations and be really smart about that as well. So it requires some basic linear algebra understanding, I think, or algebra understanding. And yeah, and so it's very important to get the basics right and to have a good understanding of, I have a tensor, what can I actually do in Torch to transform that tensor to the shape I expect, and this is something we'll be covering as well. So I could actually run the notebook, but I guess I give it a try. I feel bold today. So what's the shortcut for running? The shortcut, Shift Enter. I need two hands for that. So I don't have to go through the imports, right? That's something I like to do because sometimes some ugly warnings can just ruin your notebook. I don't like to see that, so I just ignore them. And then some of the imports I'm going through are torch-related imports. What we'll also be needing here is some SciPy for image reading, because we have images we need to be reading and transforming into matrices or tensors. And then, well, standard OS collections we'll be needing in a specific part of that code. And for plotting, well, NumPy, you always come across NumPy, you always have a need for NumPy in some of the work you'll be doing. And for plotting, matplotlib, because we want to plot the image and we want to visualize, are we actually doing the right thing or not for the model. So some of the parameters, I like to put the parameters in the beginning, so we know what are sort of the things we can change or explore. There's data involved, and I'll get to how to download that, but it's also documented in the notebook, and I don't want to download it now because I think the network is you won't finish it anyway. But you can do that if you want to look at it at home or after and see how things work. It's a 2 gigabyte or gigabyte download, so it's actually not a lot. And so there's a folder for where the JPEG images are stored. There's a folder for the labels, and we've been seeing the labels before, XML annotations. There's a standard image size we'll be working with for the data, so every image will be reformatted to be of that size, and that's something we'll be going through. The labels we saw earlier, so those are the labels we're going to predict. We need that lookup because we'll be working with a one-hot encoding, and if we want to reconvert it, we have to look up what is the label we're actually predicting. Some model parameters. So YOLO comes with basically 3 parameters for the model, and one of them I'm ignoring for the purpose of this tutorial. So C is the number of classes I want to predict, which is 20. We have the number of classes because we run on the Pascal VOC dataset, and that's actually what we want to be predicting. We have 20 classes. S is the grid, so S times S is my grid, so 7 times 7 for this specific use case. There's also parameter B, which we are not looking, which I just defaulted to 1. B is the number of bounding box predictions I do per grid. So every grid or every cell in the grid, sorry, I do per cell. Every cell in the grid can only predict 1 class. But the way YOLO is built is that it can actually come up with different suggestions for the bounding boxes for that class. And if you said B equals 2, every cell would predict 2 different bounding boxes and then predict 1 class. And then you can go with a confidence score for the bounding box to actually detect which is the one I believe is the correct one. And what happens if you do that? If you train that with B equals 2, which is the standard, but it makes the code a lot more complex, which is why I'm not doing it. And it works well with 1. If you do B equals 2, one of the predictors usually ends up being more sort of horizontal. One of them ends up being more vertical, responsible for vertical predictions. Some of the training parameters we have standard. You should be familiar with that. This is just basic neural network. We have epochs. We have a batch size. So the standard batch size for YOLO is 64. It doesn't. So I ran this on a GPU, but only at home. So I only have a GTX 1080 at home, and I didn't fit 64 images into GPU memory. I don't know why. So I just went with 16 and adjusted the learning rate accordingly. So the standard learning rate, actually, as per YOLO 1 paper, it moves a bit. I just picked a learning rate that seemed to work, and I made it a bit smaller, dividing by 4, because I divided the batch size before as well. And then devices is a parameter that determines whether I run on GPU or whether I run on CPU. Now, if you go with the Docker approach, we've been putting up for managing the dependencies, it'll be a challenge to run it on GPU. So that's meant for you to practice at home using a CPU. If you install it on bare metal and you have a GPU available, and the drivers are installed, the GPU drivers, it's actually easy, very easy to run something on CUDA. Yes, so we have. I'll be walking you through how the training works, and I can cover that there. Yeah. Okay, perfect. And so the step 1 is the data, and VOC data you can just download, and Another thing I used is that's the website of the YOLO guy author. He has a script to convert VOC labels into something that's a bit more easy to handle. So I just used that. So I don't have to do the XML parsing myself. It just creates a text file with input I'm interested in. So basically I think it's a TSV file, the format. And that's something that I wanted to pass. Correct. Next one, and I think I decided to not run it, but I could technically, but this computer is super slow. Next one is we want to preprocess the data, and we do that in a step one by filling up some lookup variables. So there's no, in the data right now, so far, there's no PyTorch involved. It's just Python magic or not magic. So we want to have images, which is a list of image names for the lookup for later on when we do the data set in PyTorch. We want to have labels, which is a dictionary from or a map from image name to labels found in that image, and bounding boxes, B boxes, which is a dictionary from image name as a key to corresponding bounding boxes found. And so we do that, we preprocess the file. It's not really anything interesting. Here happening is just plain Python, and then resulting in, again, I'll just show you some examples, right? If I take five data points for the image, I guess just a link to some of the files I have. Then for that first image, I can look up what labels are actually there. So I have labels 12 and 14. I don't know what that means, but I have the, as part of my parameters, I know what the labels are. I can do a lookup through the index, and then I can translate this into what that actually stands for. And then I can take the same image and get the bounding boxes, which I already saved in a tensor format, which makes processing easier later on. So those are the bounding boxes, and the bounding boxes, the way they work at this point, and there will be some formatting involved later, is I have the x, relative x, I have the relative y, and I have the relative width and the relative height of the image. And that comes already from the preprocessing this script I mentioned earlier is doing. So next step, I have to convert it into something I can actually work with in YOLO. And the format expected, well, you have the images obviously, but you have also the annotation or the label you're later on going to predict. And the format expected is actually a tensor of shape 730 if you work with b equals 2, which I did not, but it's a standard case, so I walk you through this. Yes. So we are looking at existing data sets, right? And existing annotated data sets, we have images, which is in the VOC data set, and we have annotations. And the annotations tell us, human annotated tell us what are the bounding boxes for objects in that specific image. So if I think the next one maybe gives you an example, like you have a bird here, and what you would actually get, so ignore some of the numbers here, but you would actually get is the location for this bounding box, and you would get the class for this bounding box, humanly annotated in that VOC data set. Those are we are looking, right, the two things. This is the metadata, human annotated metadata, which are the annotations for that Pascal VOC data set. And that's something we have to bring in a format that I can actually feed it to a neural network, and the neural network can process it. And in order to do that, I have to bring it into a tensor of shape 730. So 7 are my grids. 30 is a bit more tricky, but it's actually it's a linear, it's a vector of 5 values per bounding box I predict. So if I have b equals 2, I predict 2 bounding boxes. If I have b equals 1, I predict 1 bounding box, and each of the bounding boxes have 5 values, which again are my x, y, w, and h, so width and height. And it's also by confidence in this actually being a bounding box. And on the other side, I have 20 classes. So if I add 5 plus 5 plus 20, I come up with 30. So 5 plus 5, if I work with 2b, if I work with B equals 1, so one bounding box predicted per cell, I end up with 25 because I have 5 plus 20. 20 is fixed because I predict 20 classes, and this is all sort of lined up per each of the different grid cells in the grid. And so what we have to do is preprocess that that ground truth data we have already annotated so that I can feed it to the model. A few things we do, for example, well, I'll just walk you through some of the steps, or I could just make them here. The following steps are needed. I first have to convert the x and y, and the way YOLO works is it defines x and y relative to the cell. Or in step one, let's go one step back. The cell, I have to determine what is the cell responsible for my prediction. The cell responsible for my prediction is the cell that's in the middle of the bounding box. So if I look at this image here, that middle cell of the image, which is, I don't know, 3, for example, is the one predicting the entire object I have. So I have to determine what is the cell of my 7 times 7 cells responsible for this prediction. I then have to determine, or I then have to convert x and y relative to the cell boundaries. And if you just get that data, it's relative to the actual image. And the W and H actually work pretty well the way we get them. There's no really any formatting involved. And then I have to determine the confidence level. In the ground truth, I'm obviously 100% confident that I'm making the right prediction. And that's what I'll be working with. So the confidence level is set to 1, and then I have to well, determine what class. In a one-hot encoded sort of lookup, I have to determine what class am I working with. And this is a script that actually produces that. I don't know if well, the cell we have 49 cells available. Like if you go back, I don't know if there's a better image. Or let's assume we have 9 times 9. Let's say the green ones here, right? Which is what the example is doing. There is still a significant amount of pre-processing involved and processing through a convolutional network involved. It's not just black or white. You see there are lots of colors here. But this is still the cell predicting whether we have an object here or not. So each of the different cells is the one predicting the object. Correct. That is correct. That is correct. Correct. We have to prepare the data so that, in a way, the YOLO network expects it, so we can actually work with it. Right. So the unknowns, the output I predict is 7 times 7 times 7 times 30. Right. So for each of the boxes in the grid, I predict 30 variables. If I work with 2 bounding box predictors, or 25 variables. So those are the unknowns I'll be trying to predict. Yes, correct. And I know this is a lot to digest potentially, and this is not even the PyTorch part. But it's very specific to how the YOLO is still one of the easiest to explain, and it's very specific how YOLO expects that data format. Right? You have the data potentially in a nice format, but it may not be what the authors have found to be working well with that specific use case. For example, relating x and y to the cell, as opposed to just taking x and y from the image bottom, for example. And we do that. We bring it in a specific format. I'll be a bit faster here. There is more data preprocessing involved, but that's not really PyTorch specific. But what we want to do is then encapsulate it in a data set we can use, and Mo was talking about it earlier. So there's Torch, utils, data set. Essentially what it does is just wrapping the whole data set in an iterator. So I know I can call a next on the data set, I get the next image, and I get the next annotation, and I have something to work with. So there's not a lot of magic involved, and this is where the lookup arrays come into play we've created. So if I call next or get item with a specific index, I then look into what image corresponds to that to that index in the list I've been creating called images, and I get a specific image, and I get the targets and the bounding boxes for that image. next step is I have to, there's some formatting involved of the image so that I can actually work with it. So now we know where the image is, we know the location, we still have to read it from file system. And we do that with a function from, I think it's SciPy, with the called image read. So I have a link to that image in the file system. I read it. I do some pre-processing, and there could be a lot more to make it actually perform much better. But we do only a limited amount of pre-processing here. We do resize the image to a fixed aspect ratio or a fixed size. I think with size we had earlier 2:4, and we want to bring it to 0:1 values, the image, which is just a standard way to pre-process again. So we divide by 255 because currently it's defined in RGB, and RGB going to 255 values. And then we want to convert it to a tensor. So it's actually pretty simple. I just wrap it. Now the last one will give me, I think it's a NumPy array describing the image, and then I can just read it into a torch tensor. And then my data set would return the image read into a torch tensor and the target we've just been creating, which is the 7 × 7 × 25 tensor I'm going to predict. And then I can go ahead and say, hey, this is my data set. I can actually instantiate it. I'm just calling it VOC. I'm just touching it. I'm just calling VOC. And then there's another thing called data loader in PyTorch. And I have if I have a data set, I can just feed that or input the data set, which I just called VOC, into the data loader. I can say, what's my batch size I wanted to get out of the data set. And batch size 4, for example, is what I could use. And batch size meaning this is the number of images I get back. So if I say batch size 4, I want to have 4 images with 4 corresponding annotations back from this one here. And then I can create an iterator across it if for example, I want to do that. And did that just here. This is a function I have to detail. It's just a plot function using matplotlib where I actually use the annotations and the image to plot what we're dealing with. It's always good to visualize, and we just did that. We just get one image and target combination from the data set loader, and then we plot it, right? And when we plot it, we see this is, for example, something we get out of the VOC data set. You have, I know it's a bit small, but you have difficult to read. It's a chair, and it's another chair, and it's another chair. There are more objects here, but again, it's just 20 classes, so we do not annotate all of the objects. You could do much more. So for each of the sections, I sort of briefly describe what's missing or what's a follow-up. I'm just working with the trained data set, and every good data scientist is going to tell you, well, if I want to put this for production, I have to test it on a test data set, but it's very repetitive. It would just be the same thing. VOC comes actually with a distinct test data set, and you would just have to go through the same processing for that. And there's also data augmentation, meaning that I shift the image, or I do some computer vision magic to the image to put it into a different format and use that to predict, and in that way create more training samples for the network and make it more resilient to new data incoming. For example, what YOLO is doing, what we do not do here is random scaling of the image of up to 20% of the image size, or randomly adjust values like exposure, saturation, so changing some of the color features, or some of the values related to color in that image as well, and that will generate new and different training samples and will produce a better model if you train on data augmented data sets. We're not covering this here, and so the most challenging part implementing this yourself is actually the loss function, because that's a lot of tensor magic you have to create. You cannot. There are standard loss functions you can just reuse in PyTorch, but that's not going to work for this specific use case because it's a very specific loss function, and you have a very specific data set. And YOLO actually breaks it down into 4 different types of losses that are in a later stage only summed. And there's one loss. The loss function has to evaluate how good are you in predicting a bounding box and how good are you in predicting classes. So there's one specific term in the loss. I'm ignoring the lambda for now. Lambda is just for scale. There's one specific term in the loss that says what's actually the sum of squared differences in my x's and my y's. and that's still pretty simple. Hopefully, there's one term that may not be simple. It's that what they call one object. I'm only evaluating this for cells where in the ground truth there was actually a class, right? So it basically encourages the model to make a prediction for each of the different cells, but the loss will only evaluate whether it's correct or not. This specific loss will only evaluate whether it's correct or not for boxes that have a class. Where this comes, well, you still obviously you do not want to predict classes everywhere, but you have that's why you have a confidence term. So the idea is I want to have an understanding of, or I want to have a bounding box prediction for each of the different cells, but I want them to have the right confidence, which is another term we'll be looking into. Basically doing the same so this should read H, but I can just change it because it's not an image. It's actually all coded here. So now it's correct. It's basically the same, with the only difference that we do a root or square root on each of the different terms to sort of punish whether I predict overly large boxes. Or here, but I think it's better described. Small deviations in large boxes matter less than small boxes, but this is something where you can ignore, and I actually did that for part of the work going forward. It's just a small adjustment that maybe produces slightly better results, but it's not really critical. And then we have the confidence score, or what I said earlier, and now we have two terms, which is one object and one no object. So I want to evaluate the confidence score for every class where I predict a class. Every cell where I predict a class. I want to make sure the confidence is actually at the right level. And what the confidence on the ground truth, what the confidence score is for the prediction is actually the IOU of the predicted bounding box with the ground truth. And we've discussed those values a little bit earlier. And then in the next part, there's another term for cells where I do not predict any object, and this comes with a lambda. This comes with a lambda where I can sort of scale it. I can say how important is it for me really to have lots of predictions or not a lot of predictions. And the final one is a classification loss, which is more straightforward. And again, we only care about cells where there is a class in the ground truth, and I want to predict. Basically, what's the probability thing? But what are the differences in the probability, or what is the probability I predict minus the actual class, which would be a one-not encoded array. So it puts a penalty on wrong predictions based on how the probability was actually defined. And finally, there's a total loss, which is just summing everything together. And producing that in PyTorch is not straightforward. And I guess in none of the languages it is. And I've seen implementations with many, many lines of code. I try to keep it as simple as possible. Not covering the B term actually reduces the amount of code significantly. Because if you have to deal with more than one bounding box prediction per cell, you end up having to do lot more complicated tensor computations in those cells. And so the YOLO loss is also a module. Most of the things are module, and the module have a forward where, for loss specifically, has a forward where I give it an output and a target, with the idea that I want to process. I want to calculate the loss given what the output was and what the target was, what we just described earlier. And the first thing I'm doing is, again, this is long. I may have to go rush through some details, but feel free to question or come up with questions after, and maybe you have some time to review. The first thing I have to do is calculate my one object and no object as masks. And in order to do that, I actually sum. Or one step before, right? My target is what I said is a vector where normally I have 7 times 7 times 25, but I do have another dimension at the beginning, which is the batch size. Right now, I'm not dealing only with batches of 1, but I'm having, for example, a batch size of 4, which would feed me 4 of those images and 4 of those predictions. And what I'm basically saying is I want to understand where are my classes here. And if I do that, this is just Python. This just means take anything. I just want to restrict it on the last dimension, which are my 25 values, and I know that from 5 onwards, index 5 onwards, I actually get the class predictions. Right, 5 to 25 are my class predictions. That's what I want to return. So then that's something I store on my target, for example. And then I want to see, hey, can I sum this along a specific dimension to understand is there a class prediction for this specific cell in the grid? Because that's something I want to understand later on when I do the mass for one object and no object. So I'm having this mass based on, or do I find a value in for any of the class values I'm predicting in the ground truth, or do I not find a value? And that's something I can easily use as lookup on some of the data I get in like an output or a target. So for example, I have a target. This is my target. I have a lookup, and the lookup is just. This is also very similar to how data frames work in Python. You have just a mask with ones and zeros, or true and false, and wherever there's true, those are the dimensions, those are the values I want to keep. Whenever there's a 0, this is something I'm not interested in anymore. So it's basically just indexing. The mask is just indexing the target and the output and pointing me to the subset of cells and values where actually the ground truth has a class, and most of the computation will only happen on the subset, because that's what we did by looking at this one object earlier. And yeah, and then going through these terms, I have to maybe speed up a bit, but we start by calculating the loss x and y, and very similar, doing the same thing with w and h. Then the loss associated with confidence score has something I wanted to focus on a little bit more, because I now have to calculate the IOU. Because what I want to do is sum squared difference between confidence score and the IOU of the predicted bounding box with the ground truth. And what that means is I have a confidence score on one side, and it's a confidence score on prediction. And I have the IOU on the other side, comparing how far do I actually deviate from the object that is there. And taking that together, I can calculate the IOU and the loss later on. And for the IOU, we go through the computation. And again, it's what I want you to take away from this is I don't think it's can really go into full detail here, but there's a lot of fine-grained tensor computation involved, and you have to really look into how do I do the tensor computation, how do I do the matrix computation, and come up with a smart approach to solve this in Torch. And I know, and I see that with myself. Sometimes I just want to go back and say, hey, can I not do things easier in a for loop, and can I not do things easier using NumPy? But what you have to be conscious about is that there's an autograd feature in the background which Torch is using, and unless you use not all of the Torch computations, and definitely not the NumPy computations and loops are supported with autograd. So the moment you deviate from some of the Torch logic, there's a chance you lose the autograd feature. And what that means is the loss is not working, or you have to implement your own backward. So now we're only implementing the forward, but the back propagation is something that comes for free if you implement it the right way. If you don't, it will not come for free. And then you have to really think about how to do the back propagation, something I do not want to think about. For it can get really complex for something like that. And I do that. I calculate the other loss terms. As a classification loss is probably the easiest, because that's more of a standard classification loss. Yes, please. Correct. But it is a mask, right? Or did I not get the question correctly? Because what I do is I calculate it as a it's a mask I produce, and then I use this mask to produce a view on the tensor I'm using then for computation. It's not what it's not doing. It's not copying. Right, but it's not doing a copy of the tensor. I'm not copying the tensor. It's just producing a view on that same tensor based on the mask I input. So I think I understand the point. Sorry. And I am not sure I understand how that would be different. I guess I could solve it with multiplications as well, but I don't get the issues with using a mask here. If I would understand if it would produce a copy of that tensor, which is obviously not really efficient computationally, but are you saying multiplication is potentially better than the lookup with the mask? Did I get that right? Right. So this is a lookup based on the index, and there's a chance that multiplication is actually more efficient or something that. But I think most of the work computationally will actually happen in the network and not as part of the loss processing. So we may be optimizing in a very small area here. Because what I ended up doing is when I run this, the loss I run on CPU and the network I run on GPU, and really the other part of the network is what slows things down, not necessarily the loss. But yeah, there is potentially a way to solve with multiplication. I agree. This is just the dimension I'm using. It's a real sum. I sum the values I have in the tensor on dimension 3. Yeah. It's a bit difficult to describe, yeah, but it's the third part and I have in the back. There's the cell. Okay. Now we have a loss function that is implementing the YOLO loss, and that's something we can use to train the model on. But before we do that, we have to initiate it or instantiate it. So loss is my YOLO loss we just built, and going back to the iteration we had earlier, I can actually try and see whether the loss produces something, and that's what I did here. So if I take the same sort of data points, I obviously expect if I compare them that there's a zero loss because it's exactly the same type of data, which is just a very simple test, but it works. And then if I go and produce randomly different, there's no prediction. I'm just taking 2 random images as target from my data set, another 2 random images and annotations as output from the data set, and I'm just randomly comparing them. So there's obviously no overlap intended, so it ends up producing a very high loss because there's no prediction involved. And that's basically it. So the next part we look into is creating the actual model, and most of the work, as I said earlier, was producing the loss. The model is comparably easy because what you can do is, or you use a pre-trained model from torchvision.models, which comes with a lot of different pre-trained models, and I used the VGG16 as a feature extractor. It comes with 2 parts, and the final part of that architecture is called classifier. And that's those are 2 layers, and those 2 layers is something I want to replace with my own implementation, or something that works for my specific use case. And specifically interesting here, the layers is just what YOLO is doing and has proven to be working well. Interesting is the final linear layer, which is supposed to produce the data and the output format I'm expecting. And so what it does is it takes an amount of values in, and the output I'm expecting again is my s times s times 5, and the number of classes I have. And it's producing it as a linear layer. I have to do a view operation later on if I want to bring it into the tensor shape I was working with earlier again. But for this specific purpose, that's okay. And this is I can easily print the architecture it produces. So this is just VGG, or one version of VGG. There are different sizes and shapes as well. I don't know if I mentioned that, but if you pre-trained 2, I think Mo was talking about it earlier, gives me the weights for free, and then that is great because then I don't have to train it myself. And if you do it, it downloads it once the first time, and then it doesn't have to download anymore because it stores it somewhere in the computer. You can actually work with it. So that's what we did here. It downloaded the weights. One thing we want to do though, one point I did not mention, I think it's also interesting. I can make a decision on whether I want to exclude sort of the first layers from the gradient update or from the training process or not. And I mean, ultimately, I would see what works better. That means, do I just take that part of the VGG network and work with what it outputs, or do I want to fine-tune it for my specific use case? In this specific case, we fine-tune it because that's what YOLO is doing. But I could also just use them the way they are, and we'll probably still get to meaningful results. And I do that by setting requires grad is false. So that means gradient computation is not required for those layers in the feature layer, and it's a reasonable approach to do that as well. This I can next one is and this is again going into some fine-tuning tasks. I want to potentially change how some of the weights are initialized in some of the newer networks I've been producing, because I removed them and I added new networks and they come with their own weight initialization. Maybe I want to do a different type of weight initialization, but that's optional. It could hopefully speed up the training process a bit if you are smart about how you initialize the weights. And the final part of this is then I would go and train the YOLO model. And just sort of to wrap up what we've done before, we have a train dataset now, which is a dataset class implemented in PyTorch. And then again, I wrap that and put that in a data loader, so I can iterate for the datasets based on the batch size I set. I use the batch size I defined earlier in the parameters, which is 16. For this specific case, I can define whether I want to shuffle the data or not, which is a neat feature to have. For some of the output I produce, I need to know what is actually, how long is a batch for me? So what is the length of training data? How many batches do I have in the entire data set? It's basically what that says. And I want to have my loss, which I call criterion here. And I want to have my model. And again, earlier I said I can use it on GPU, which if you really want to train it, you have to do it on GPU. On CPU, it's just taken ages to do that. I tried it actually, but then I quickly switched to training it on GPU. You have to define an optimizer, and I go with the standard choice here, which is an Atom optimizer, and the optimizer will take the model parameters, which is the parameters the optimizer actually has to optimize as part of the process. And the learning rate we said earlier as well. There is some smartness about changing the learning rates during training process in the YOLO paper, which we do not do here, but it's fine. It still works reasonably well if you set a smallish learning rate and have the model go with that. And so the training process, we iterate over epochs, and I think there was a question earlier. So one epoch is one iteration over the entire data set, and it produces batches. So batches, what's my intake in images and targets per iteration. For each of the batches, I sum, or for each of the epochs, I sum the loss over batches, and then I output it. What I do during the batch is two things. I have to go first to a forward pass, so that's a little bit PyTorch specific. It would look different in TensorFlow. You have to define the forward pass. So while this is ignore this one, it doesn't really mean anything. There was an operation before which I did not remove. Step one is I have to get the image and I have to permute it in a bit, and this is just simply because PyTorch or the actual model expects a different formatting in the image, and I have to change some of the layers from NCHW to NHCW or something. So there's a shifting. I have to just reformat the image so it can actually be worked with in that specific case. And then I send that image of vector or image matrix or tensor ultimately to the device I define. So I can send it to GPU. So all of the computations on that specific a tensor are going to happen on a GPU, which is pretty simple, pretty straightforward. And then I go with the model, and I have to give the model the image to train on. And what I expect as an outcome is the predicted target. And again, the shape is 7 times 7 times 25, but linearized, so about 1,000 something values if you multiply, or 1,000 values. And then I have to, because it's linear, I'm doing the view operation, so I bring it back into that shape, 7 times 7 times 25 tensor. And that's something I can now feed to my loss operation. Again, it's a forward. What I do is I compute this on a CPU. There's not really any specific reason to do that, but showing you that you can easily compute something on a GPU or whatever device you define, and that moving it back to CPU by calling CPU on that operation. So in that specific process, the outcome, the output of the model would be moved back to memory, and then that's where the compute is happening. And the target I get, now I want to compare, or want to get what's actually the loss of those two if you compare output and target, the loss function we were discussing earlier. And once this is done, and Mo has sort of walked you through some of the basics of the training process in PyTorch. I have to set all the gradients to 0 because that's not automatically done. I have to do a back propagation based on the loss I just computed. And then I have to call optimizer step. So optimizer step can adjust based on that back propagation. It can adjust the parameters accordingly. Yes. Correct.